All right. We are going to spend some time today on some difference in double angle identities. I'm just going to wait to see if we can get a few more on here before I get right into it. So what I want you to do is copy down a sheet of all the identities. I'm going to grab the one out of the exam booklet. Okay, so, I still have one more of these, but I'll wait do the double angle ones tomorrow. But what I've just written down are all of the identities that are given to you would be given to you in the exam booklet. So the best thing that you can do is keep these on a separate piece of paper beside you when you're going through and working through these questions. Um, this is one of the more difficult things that you're going to do. So what I think I'll do today, maybe as opposed to going through 6.2 with you, because we have some time, a little bit of time to spare, because we don't have to rush for that provincial exam. I think what we'll do is we will go through and do a good job of these 6.1, 6.2, and 6.3 so that you have a good grasp of it, because this is real. It is something completely different than what you've done to this up to this point. Those of you watching live, I'm also live on Microsoft Meetings. So if you want to come on the meeting right now and join, that would be a good idea. And then we can answer questions from yesterday's work. So it's up to you. But if you want to get on the meetings, that would be a good idea. All right. So these are what we call, these last ones are what we call sum and difference identities. And these are out of 6.2. And again, the reason why we do this is because if you look at the bottom of the page on page 197, you see all of the exact values from around the circle for all the 30s, the 60s, the 45s, the 90s, and so on. All of those angles, we know all the exact values of those angles. But what happens if I want the exact value of something like this? And I did this yesterday where I said, well, okay, I want the exact value of the sine of 15 degrees. Well, I don't know what the sine of 15 degrees is. So I'm going to change it to sine 45 minus 30. Now here's the first error that gets made that we have to make sure that we don't make this error. This is not sine times that. Sine is a function itself. It works like multiplication, addition, subtraction. It's a function. So we don't take this and distribute it through. This is a function. So what we do is we use our sum and difference identity. So we go, and I think I wrote this maybe wrong yesterday. So it's sine 45 degrees, cos of 30 degrees, subtract the sine of 30 degrees times the cos of 45 degrees. So this again is called an identity. It allows us to be more precise, to work with exact values and not have to work with decimals for this. And the identity works like an equation, but in an equation, you're assuming that you're going to solve one or both sides of the equation. In this is just used to change the form so that it's something that is easier for you to work with. So for example, I take sine 15 degrees and I can change it into sine 45 cos 30, subtract sine 30 cos 45. And then at that point, I put in my exact values. The sine of 45 is root 2 over 2. The cos of 30 is root 3 over 2. Okay. All right. All right. And then I go subtract 1/2 times root 2 over 2. So what I get for the sine of 15 degrees would be root 6 over 4 minus root 2 over 4. So the exact value, if you were to punch it into your calculator, of course, would be sine 15. Or I would expect, which would give you a decimal, okay? But the exact value of it is root 6 subtract root 2 over 4. So what an identity is it's an equation, even though I don't like to call it an equation. It is used as if it's an equation to help solve a problem that we don't have the exact value for in terms of trigonometry. Okay? Well, that's why that didn't work. Okay. Sorry, I gotta go back. Damn it. All right, try getting on that again. I didn't do that right. So if you can get on to meetings right now, go on to meetings. It should be under Pre-Calculus 40S. Try that again. Okay, there you go, Rory. Okay, I think, yeah. Hi, Mary. There you go, Rory. Okay, Rory, you have to delete or mute the YouTube video. Okay, Rory, you have to delete or mute the YouTube video. No, don't mute you. Mute the YouTube so you don't get.
Now I know, I got her now.
Okay. Okay, so I've got two of you on right now. All right. Basically, what I want to do this morning is go through yesterday's more than anything, so that you have an understanding of it, and then I'll do more on 6.2 tomorrow. But I was waiting for people to come on here. I did this with the grade 11s this morning, and I had about 6 or 7 grade 11s on here while I recorded it on YouTube. I had them live. It worked way better. Okay, so when I start the YouTube live, I'm going to open up a meeting as well at the same time. All right, so did you have questions that you want to look at from yesterday's work? Did you get it? Understand it?
I'm working on it.
Mary, how did you make out yesterday?
I didn't get a lot done, but I watched the lesson, went through the examples and stuff.
Okay.
Maybe we could go through a question or something.
Okay, just a second here. Okay, well let's go through. I'll do one from each of them. Okay, so first thing it says is determine the non-permissible values of x in radians for each expression. So I'll look at 1C to begin with. Okay, so basically what's happening here is I want to break it down into sine and cos if I can to start with. So cotan is cos x over sine x, and all of that is over 1 plus sine x. Okay, so the non-permissible values. So basically what's happening here. Okay, David, turn the volume off on the YouTube. Okay, perfect. Okay, and I can hear you today, so you fixed your volume.
I use my cell phone.
Okay, perfect. Okay, so when I'm looking at non-permissible values, I'm looking at the denominators on all of the fractions. So that means then that sine x can't equal 0, and 1 plus sine x can't equal 0. So then you have to tell me, okay, for what value of x does sine x equal 0? So where on the unit circle does sine x equal 0? So have your unit circle out beside you.
Pi divided by 2.
For sine?
Wait, it goes cosine, right? Oh,
right.
No, sorry. 180. 0 degrees.
0?
2
Mary said 180 and 360, right? So for every 180 value, you would have that, right? But it asked it for in radians, so I do need to switch this out. So I go 0, pi, 2 pi, right? Okay? And then when I do this, where does sine x equal -1? So what value, what degree value in radians does sine x equal -1?
3 pi divided by 2.
Perfect. 3 pi over 2. Okay?
News, I can't see you, and I don't know why.
Can you hear me?
I can hear you, but I can't see what you're doing.
Okay, do you have the YouTube up right now as well?
Wait, let's look. I don't think so. I'm gonna go check.
I find that it's easier to see my board if you have the YouTube on beside you. I know the grade 11 said this morning it was hard to see the board.
No, like I can't see anything. Like I see JN and a blank screen. I don't see a board. I don't see anything.
Well, I can
Can you
see
hear me?
I can see you. I can see Daylin. I can't see Mary.
I can legit just see myself.
Okay. Well,
Oh, there you are.
all right. You okay?
Yeah.
Mary's texting me.
Okay.
Oh, just kidding, Daylin's back.
Okay. So, are we following? Are we good to go here? Yeah.
I'm looking at Daylin's face right now. I'm not gonna lie.
So you don't have all 4 of us on the screen? There's only 4 of us in this conversation. Okay, my thing just clicked off. There, I got all 4. I got the 3 of you on my screen now. So what I want you to do is just mute. Put your mute button on for right now. All 3 of you. Okay, good. So now it should be only me that pops up on your screen. So, okay, so back to this. What's your problem, Rory?
Because I'm seeing your initials. I'm not seeing the board or anything. I'm seeing like your initials.
Okay,
in the middle of the screen.
Can you follow on your computer?
I'm trying. Okay, let's hold up.
The other 2 girls can see the board fine? Just give me a nod. Okay.
I love how my laptop does that.
All right, Rory, you keep working on it. Okay, so the one thing I didn't do with you yesterday that I need to do today is to show you how. So I've only gone around the circle 1 time to where the non-permissible values work. So to write this proper for my non-permissible values, instead of writing 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, I have to write it like this. K pi, where k is an integer. So that means 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 0 pi, -1 pi. So wherever I have a pi value, that's where sine theta is going to equal 0. Okay? And then on the next one here, x can equal 3 pi over 2 plus 2k pi, where k is an integer. All right? So 3 pi over 2 plus 2k pi, that just means that I keep going back around the circle to 2k pi every time. So I keep going 2k pi to get back to 3 pi over 2. All right, so we did this in the last section, okay? It was hard for us to understand then. It's probably going to be hard for us to understand now. All right, but this is the correct answer for it if you look in the back of your book as to where all the non-permissible values are. And that is because I have a denominator here and a denominator right here. I have those two denominators. So that's why I have to find out what value of x would make that equal to 0 and what value of x would make that equal to 0. All right, now, let me explain this the way I would have explained it to you last year. Last year, because I'm doing this with the grade, I'm doing this with the grade 11s right now. So last year we would have an expression such as x plus 2 over x minus 1, x minus 3. For what value of x down here will I get a non-permissible value? Which means for what value of x am I going to get a 0 in those brackets and a 0 in these brackets? So I go x minus 1 can equal 0, x minus 3 can equal 0 to solve this, right? Therefore, x can't equal 1 and x cannot equal 3. So if x is 1, I'm going to get a 0 here. If x is 3, I'm going to get a 0 here. So how is this different than what I'm doing right now? I'm using sign values now. So sine x cannot equal 0. All right, if it equals 0, I would get 2 over 0, which is undefined. I can't have that. So I go 2 over sine x. Therefore, sine x can't equal 0. Well, I need to know, well, that's fine, but what value of x is going to give me a 0 there? So I go x can't equal 0, pi, 2 pi, and it would go forever. So how do I write forever here? I write it like this. K pi. So wherever I end up with a pi, it's either 0 pi, 1 pi, 2 pi, 3 pi, whatever that is, it doesn't matter. X can't equal it, or I'm going to end up with an undefined value. So I get, that's how I'm evolving from this to this, from grade 11 to grade 12. Okay? Again, I'm going to show you an example of a question that I did this morning with the grade 11s. Okay? And then I'm going to make it make sense for what you're going to do today. So just let me find an example in the book here. Okay, so last year I gave you this. X squared subtract 1 over x squared plus 3x plus 2. And I said, okay, this is a fraction, so I need to reduce the fraction. All right? So the first thing that I would do is I would factor it. So I wrote it out like that, right? Okay. Then I would say, okay, after I've factored it, find my non-permissible values. So x can equal -2, x can equal -1, because if this is -2, that makes this 0. If that's -1, that makes that 0, so we can't have those. And then at that point, I just reduce my fraction by canceling top and bottom. Just like that, right? So I end up with x minus 1 over x plus 2. So the simplified version of this would be, so that's what we did last year. Okay, so I'd have x minus 1 over x plus 2, where x can't equal -2 and -1. So this is all this is just taking a polynomial expression and reducing it into its smallest. And we're going to do this again next unit, probably in grade 12. where we have to graph it. So we have to work with this. Okay? So this is where I'm at right now. Today, I'm now giving you sinusoidal expressions such as this. And I'm saying, okay, I want to reduce cotan x sine x. Writing it in its smallest terms in terms of sine and cos. So cotan x is cos x over sine x. Okay? Times sine x. Just like that. All right? My non-permissible values. Sine x can't equal 0. Therefore, x can't equal k pi, where k is an integer. And now that I have my restrictions or my non-permissible values, all I do is cancel out. That leaves me with cos x. So there's my solution. So that's looking at 2a. All right. So what I'm doing is I'm taking sinusoidal expressions now, not polynomial expressions, and I am reducing them. So into smaller terms. Okay, so I'm going to look at 2c now. Any questions about this? No? Okay. I'm going to look at 2c. So I have cotan x, tan x, over cosecant x. All right. So let's put them all in terms of sine and cos. Okay, so I've reduced them. I put them in terms of sine and cos. All right. My non-permissibles again, wherever my denominator can equal 0, so I have to find out those. So sine x can equal 0. And we already know that that's at k pi, where k is an integer. Cos x can equal 0. Well, this one's a little more complicated. Cos, so all of the odd pi over 2's. So I write it like this, 2k plus 1 pi over 2. The 2k plus 1 represents odd numbers. Because if you multiply any number by 2, it becomes even, right? And then if you add 1 to it or subtract 1, it would always end up being odd. So that's how I write an odd value, 2k plus 1, and then pi over 2. You got to unmute, Daylin. Daylin, you're muted. There you go.
Is that like also how you get like your asymptote sometimes?
Yes.
Like on the last unit, that's how you got your asymptotes for like the tan graph?
That's exactly right.
2k plus 1 times pi over k.
Yeah, absolutely. Yeah. Okay. And then again, I just add k as an integer. So I've taken care of my non-permissible values. Now I need to simplify my fractions. Well, that times that is 1. So I'm left with 1 over sine x, which is just sine x. I just reciprocate 1 over this back to sine x. Okay? All right, and then my non-permissibles I would add in there as well. So 1, 2, and 3. 1, 2, and 3 are all just simplifying these. That's about it for that, I think. It obviously gets much more complicated than this, but I don't think we need to be as concerned with this graphing of this, especially considering we're not having to write it on the exam. I don't think we need to focus on graphing as much. What I want you to focus on is the algebra part of it. So I'm going to leave it at that for now. Let's I'll let you work on, like, basically I want you to complete to the end of 4 on that section. And then maybe do question 7 as well. Okay, that's kind of what I want to see for that. Let's go through 6.2 now. Just the start of it. I'm just going to give you the very basics of it. What I want you to do at some point today is either write this out, okay, from your book, or go to the exam website, the Government of Canada, the exam website, and print off the equation sheet that they give you out of the exam. So show you that there. I would print that off, okay? Or what I'll do, actually, maybe, why don't I take, well, no. Go to the government website where you find the archived exams and print that off. That would be your best bet, unless you want to write out all of these identities. Okay, but in order to do these questions, you want to have them beside you. All right. So the reason that we use them, again, is so that we can find exact values of angles that aren't on our unit circle. All right, so the only thing on our unit circle is 30s, 60s, and 90s. What happens if we want to find something that's not on the unit circle, like a 15? Okay, so I use an identity to help me do that. So what they want you to be able to do is write out these as single identities. So take a look at page 198. It has this written down: cos 32, cos 50. Plus sine 32 degrees, sine 50 degrees. Okay, and they want you to write it as one singular identity. So flip back a page. Flip back to page 197. And look at the sum and difference identities and find the one that goes cos, cos plus sine, sine. So find the one that goes cos, cos plus sine, sine. All right. I get agreed? Alpha minus beta. Okay. So then that's the cos of 32 degrees subtract 50 degrees, which is the same as the cos of negative 18 degrees. Okay, so hypothetically, if you were to punch into your calculator cos 32 times cos 50 plus sine 32 times sine 50 and hit equals, you would end up with the exact same thing as cos negative 18. We call this identity because this is exactly the same as that. This is a simpler way of writing it as a single trigonometric identity. This is how you would expand it out. Okay? So we have to work back and forth. All right? If you follow through in your book and just write in and fill in the blanks there, you got cos 32, cos 50 plus sine 32, sine 50. It has the same form as the right side of the difference for the identity cos alpha minus beta. So then you would fill in cos alpha minus beta. So that's cos alpha, cos beta, plus sine alpha, sine beta. The next blank would be cos 32 degrees subtract 50 degrees, which would give you the cos of negative 18. Okay? So like I said, if you punch that into your calculator, this would equal what that is there. And again, we're just writing these in forms that make the question simpler for us. So the next one is find the identity that is 2 tan pi over 6, 1 minus, and it says, so that's the same as tan 2a. Or in this case, my a value is pi over 6. So I'd have the tan of 2 times pi over 6 which reduced is tan of pi over 3. Sorry. So following in your book, you'd have tan 2a is equal to 2 tan pi over 2 tan pi over a over 1 minus tan squared a. Therefore, tan 2 times pi over 6 is the same as tan of pi over 3. Okay. I'm going to be honest, this is probably one of the hardest things to teach the way we're doing it right now. Okay. We'll do one more anyways, and then we'll do the rest tomorrow. Consider the expression sine 2x. You know what? I'm going to leave that there, girls. I want to start right there tomorrow with the double angle identities. So what I want you to do today would be to finish 1 to 4 on page 192 and 193, as well as question 7. And then you could do the algebra part on 8. And that would be it for now. Okay, end the stream here. What I'm thinking